we're on to like one of the last topics, which is matroids. We're going to spend some time on this because there's a lot of stuff to build up. So first, let me define a matroid. The definition is probably not going to be very intuitive, but then once we see a few examples, hopefully it'll get a little bit better. So for a set, let's say x, let's define the power set of x. And the way I'm going to write this is I'll write 2 to the x as the power set. So it's a set of all sets A such that A is a subset of X. Okay. Probably in some courses you've used different notation like P of X or something. I guess I'm just using this notation because it's, I don't know, I find it kind of more useful to, because, I mean, of course, the power set of x has size 2 to the power of the size of x, and I don't know, it's kind of, anyway. Okay, so let me tell you what a matroid is. So, a matroid, actually, have any of you ever heard of a matroid before? Okay. It's kind of a, okay, it's a, well, here's the definition. So it's a pair x, comma, like script kind of curly I, where x is a finite set. And I is a subset of the power set of x. Okay. Such that 3 conditions hold. So the first condition is that I don't want I to be like super trivial. I don't want it to be the empty set. So I want it to have something in it. And I guess like a, I mean, as we're going to see, like a natural thing to say is like an element of this is the empty set itself. So I'm going to say the empty set is an element of I. And this just avoids making this set completely so this avoids the situation where the whole collection is just empty. So this is not like a terribly interesting condition, but it's kind of useful to assume it. The second condition I want is that this collection is downward closed. So if you have a set that's in the family, then every subset of that set is also in the family. Well, the family, I mean I. So if, let's say, Z is an element of I, and Y is a subset of Z, then Y also has to be an element of I. So this all just like, in other words, this means that the collection is downward closed. Sometimes people will say, like, for this, like, I is a down set. Right, so down set just means, like, it's a set where if you take anything in it, a collection of sets where if you take something in it, take a subset, it's like closed downwards, right? By the way, once you have the first two conditions, it's kind of clear that this, really what this first condition is just doing is it really is just avoiding the case where this is empty, like, because if I contains any set, then it will contain all the subsets of it, so it'll contain the empty set. So as long as, like by the second condition, so as long as this is not the empty collection, it'll contain the empty set, right? So anyway, that's all this is saying is we're not taking the empty collection of sets. The third condition is the actually interesting one. So it says that if you have two things, y and z, that are in I, such that the size of y is less than the size of z, right? So I've got two things in the family, one is bigger than the other. So the kind of key condition is that there should be something that's in z but not in y that I could add to y and then stay a member of the family. So then there exists an element, little z, let's say, in capital Z minus y, such that y union little z is an element of I. Okay. So when we have a matroid, we often, there's some, so just kind of terminology. So for a matroid, let's say M, which is xi, we say, so X is called the ground set. Of M. The sets in I are like independent set. So these are called independent sets for M. Okay. And if you have a set that's not independent, then naturally it's called dependent. So the sets in 2 to the x minus I, so all the things that are not independent, are dependent sets for the matroid M. Yeah, so right now this is just like a definition, and like without any context, it's not really clear why I would care about this definition. But so there's a reason, by the way, that we use these words independent and dependent. It comes from like the kind of one of the most standard examples of a matroid, which is a set of vectors in a vector space. So if you take a set of vectors in a vector space and you define independence and dependence appropriately, what you get is a matroid. So as an example, so let X be a set of vectors in a vector space. So it could be like Rn, it could be a complex vector space or a finite vector space, like for a finite field. I really don't care what vector space it is, just any vector space. So now we could let I be the set of, well, the collection of subsets. Let's say A is a subset of X, where the elements of A are linearly independent. Okay, so I claim that the pair x comma I is a vector space, not a vector space, a matroid. I guess I should make X a non-empty set, but anyway, doesn't really matter. Or maybe that, maybe even that doesn't. Anyway, let's just make it non-empty. Otherwise, it's not very interesting. Okay. So, okay, I want to show that this is a matroid, but first of all, like, I think this example kind of explains why we use these words independent, because it's like you should think of an independent set of a matroid as kind of being like a set of linearly independent vectors. Although when we move past this example to other examples, it's like it's not exactly the same thing, but it's kind of a generalization of that concept. Also, I think this might be, I don't exactly know where the word matroid comes from, but I think it might be from this example as well, that instead of thinking of a bunch of vectors, you could think of those vectors as forming the rows of a matrix or something. And then this structure, this matroid, like captures the linear independence between rows of that matrix. So it's kind of related to matrices, so it's a matroid. I don't know. I didn't come up with it. Okay, let's see that this is a matroid. So, okay, so like the first two conditions are usually pretty easy, right? So for condition 1, well, I mean, the empty set is a set of linearly independent, like it doesn't have any linear dependencies. If I can't get a subset of these vectors who have that have a non-zero linear combination. So this is linearly independent. So condition 1 holds. For condition 2, it's also pretty easy. Like if I take a bunch of linearly independent vectors, I take a subset of them, they must also be linearly independent. So linear independence is preserved by taking subsets. For condition 3, so this is always the one that is like, I mean, probably 90% of the time, this is the one that's like more tricky to check. But so here we have to like actually think about some linear algebra. So let's say y and z be elements of I, where the size of y is less than the size of z. Okay, so these y and z are both sets of linearly independent vectors. And there are more things in z than y. So I want to find an element of z that I can add to y while keeping it linearly independent. Can anyone see why I would be able to do that? Just thinking about, like, I don't know, linear algebra, maybe dimensions span, like geometry of it or something, I don't know. So like, I don't know, if you think of the things in y, like if you think of the span of those vectors, like the dimension of the span of the vectors in y, well, these are linearly independent, so it should be like y, right? And like same with this. And like, if you think about it, I mean, so yeah, this spans like a size of y dimensional space. This is a space of dimension the size of z. And like, all of the vectors of z cannot live inside of y, right? Or sorry, what am I saying? Even in this, yeah. So there must be some z in z that is not in the span of y, because otherwise, in other words, if every vector in z was in the span, so what, you know what I mean when I take the span, right? Like take all the linear combinations. If everything in z was in the span of y, then the dimension of the span of z would be at most y, but it's bigger than the size of y, right? So now, yeah, pick such a z, and you get that y union this z, this little z, is linearly independent. Right, so for example, imagine y has size 2, z has size 3, then y will span a plane, and z will span a three-dimensional space. But that means like it couldn't be the case that everything in z was in that plane, because then it would span the plane as well. So there has to be something outside of that plane, and that's the thing I can add to y while keeping them independent. Okay, so this is a kind of special class of matroids called a linear matroid. Okay, so any matroid that you can get from linear independence of vectors, yeah, it's called a linear matroid. Okay, any questions about this one? Okay, so a little bit more terminology, which is again going to be inspired by linear algebra. So for a set, let's say y, which is a subset of x. So here we're always going to be in a matroid. So x is like the ground set of some matroid. A basis for y is a set B, let's say, which is independent, so it's in I, such that so B is a subset of y, and it is maximal with respect to these properties. So, and there does not exist some little y in y minus b such that B union y is independent. So in other words, it is a maximally like independent subset of y. Okay, and then I guess it's kind of clear why we use this word basis. It's like very much like a basis of a vector space in linear algebra, right? A maximal linearly independent set. Okay. So here's a first kind of fact, which I guess kind of generalizes things you've seen in linear algebra. So you know that if you have a vector space, all the bases have the same size, right? In the same way, in a matroid, for any subset y, all the bases for y have the same size. So for any matroid, xi, and any subset y of x, all bases for y have the same cardinality. Okay. And this is for any matroid, right? So not just these linear matroids. I can't remember if I put this on your assignment or not. I might have, but it's kind of an easy argument. Like, can anyone see like how you would do it? So suppose I take two different. I take a set y, right? I take two different maximal independent sets. Let's say B1 and B2 inside of y. So I guess, suppose they're different sizes. One's bigger than the other. Like, so I want to prove that whenever you take maximally independent sets in some set y, I want to show they have the same size. So if they don't, then one is bigger, right? How would I use that to get a contradiction? And you have to use the fact that this is a matroid. So suppose B1 is bigger than B2. Any thoughts? I would kind of, well, maybe like, we want to use something on this list of conditions, right? Yeah, because it's supposed to be maximal. Yeah, exactly. So just take something from the big one, put it in the small one. One small change I would say to that is, I know over there we were talking about linear independence for these linear matroids. Here it's just dependent, which could mean a different thing in general. Like, we'll see more examples of matroids. So yeah, technically it's not linearly, but anyway, that's the idea. Take something from the big one, put it in the small one, and yeah, it's not maximal. Okay. Okay, so now that I know that any two bases have the same size, I can like define a number that represents that size. Okay, and this also comes from linear algebra. So the rank of a set y in X is the cardinality of a basis for y. Okay, and I don't have to tell you which basis, because like we just said, they all have the same size. So just pick any basis, and that defines the rank. And the notation is, so if the matroid's called M, then my notation for the rank would be Rm of y. Yeah, so it's kind of unfortunate that like I have to just keep giving you like we can't do anything until I give you a lot of definitions. So I'm going to give you one more definition. A circuit in a matroid. So a basis was like a maximally independent set. A circuit is going to be a minimally dependent set. So it's a dependent set C such that, like, if I take away an element, so C minus X for some, is independent, so it's in I for all X in C. Okay. So yeah, this is a separate thing here at the bottom. So yeah, it's a minimally dependent set, which is it's going to be somewhat different than a basis. Bases always have the same size, but circuits could be of different sizes. Okay, let's see another example of a matroid. So then we can see that this is not just about vector spaces. There are other examples. In some sense, the concept of a matroid is almost too general because it makes it hard to get like a handle on what it is, but it's good to be very general because then if you prove something about matroids, it implies things about lots of different structures at the same time. Okay, so here's another example of a matroid. This one's coming from graph theory. So a forest, you might know, is a graph without cycles. So it's an acyclic graph. Okay. It's kind of like a tree, but a tree has to be connected. A forest is like a union of trees, right? So it's, it's a bunch of trees kind of put together. And it could have isolated vertices and whatever. Okay. For a graph G, so a spanning forest, in a graph G is a forest F, which is a subgraph of G, and this word spanning means that like it has all the vertices that G has. So the number or the set of vertices of F is the same as the set of vertices of G. So yeah, if this was my graph G, and this was, let's say, F, then this would be a spanning forest of G. Right, but if I took away some vertex, like then it would not be a spanning forest, right? It needs to contain all the vertices of G. Okay. So here's an example of a matroid, and then we'll explain why it is a matroid. So let X be the set of edges of G for some graph G. And let I be the set of all, let's say, Y, which is a subset of the edges of G, such that the graph consisting of the vertices of G and then the edges that are in Y is a forest. Okay. So in other words, basically the independent sets in this matroid correspond to the sets of edges that make spanning forests of G. Right? So for example, if I had no edges, like if you take this graph, you select none of the edges, that gives you 5 isolated vertices, that's a forest. Right? So that would be an example. And obviously, if I take any forest and I delete some edges from it, it's still a forest. So like this thing's going to satisfy the first 2 conditions kind of trivially. So really the question is, so we want to show that this is a matroid. So we need to show, so to see that xi is a matroid, we verify the third condition, which, yeah. So yeah, this one. Because yeah, like I said, the first 2 conditions are pretty easy. Okay. So what I want to say is that if I take 2 sets of edges where each of them makes a spanning forest, or each of them makes a forest, if there's more edges in Z, like let's say these sets are called Y and Z, so 2 sets of edges, Y and Z, Z is bigger than Y, then there should be an edge I can take from Z and add it to Y to maintain the property that it's a forest. Okay. So I don't know, like as an example, so let's say these white edges form, like the white edges are Y, and let's say that the green edges are Z, and let's say, I don't know how, yeah, I guess I put 5 of those, so I need to put like at least 6 of the other one. And let's say there are more vertices here, so like I can, and Y and Z could have some edges in common. Like, so maybe this one's both colors. Well, okay, I've made my, okay. Okay. So, okay, I mean, so I think, yeah, Y is so this edge is in both. I don't know how to draw that. But yeah, so Y has 5 edges, Z has 6. In this case, I guess it's kind of obvious how I would add an edge to Y to keep it a spanning forest, because I'd take that one, because that one's just sitting by itself, right? Imagine I color that with white, then the white edges still make a forest, right? But the thing is, like, no matter what I do, oh yeah, or I could have also taken that one, right? So here, actually, I've got some options. Yeah, I could have taken that one, I could have taken that one. I guess also I could have taken that one. Like, I don't know, if I'm more kind of careful here, like, you could get into almost get into trouble. Like, okay, suppose Z, okay, so far it's got 3, 4, let's say that one makes 5. So now they both have the same number of edges, but there's nothing I can add from Z to Y to keep it a forest. But the thing is, Z has to be bigger, so like there has to be some other edge somewhere that essentially, so now I could add that one, right? If you think about it, the point is that if Y and Z both make forests, and Z has more edges, then Z is going to have fewer components. So, since Y and Z make forests in G, we can say exactly how many components they have. So like v of g comma y has number of vertices of g minus size of y components. You can think about, like, yeah, this is going to be true for any tree, right? Or for any forest. You could think about this like adding one edge at a time, right? So if y had no edges, then there'd be number of vertices components. If I add one edge, that merges two components. It reduces it by one. Every time I add an edge, since I'm not making any cycles, every edge that I add will merge two components and drop the number of components by one. So, and so also v of g comma z has number of vertices minus z components. So if the size of z is bigger than the size of y, then, so maybe I'll call these graphs gy and gz or something, or maybe fy for forest. Then fz has fewer components. Than fy. So from this we can get that there must be two components of y, of fy, where there's an edge of z that joins them. Right? Because if there wasn't, like if I look at the components of fy, and if all the edges of z are just inside of those components, well, like, then they would have the same number, like z would have only more components than y. Like if all the edges of z were just inside of these blobs, then it couldn't have fewer, so yeah, there must be some edge of z that goes from a component of y to another one. That's the only way you can have fewer components. So yeah, so there exists an edge E and Z between two components of fy, and then like adding E to y maintains a forest. Right? Because it doesn't close a cycle because I'm adding an edge between two different components. There's no way I could get a cycle from that. It's a little bit sketchy, but that's the idea. Okay, so it's kind of the same idea as the linear matroid as well. Like in the linear matroid, you kind of look at the span, and then you say, since x is bigger, there's something kind of outside the span. Think of these components as sort of like a span in some sense. And then I'm just saying, okay, since z is bigger, it must go between two of these. There must be some edge going between two of those components. Okay, this example is something called a graphic matroid. So maybe here's a question. Suppose the graph G is connected. Let's say, just to make our life simpler. What would be a basis for this matroid? And when I say a basis for the matroid, I mean like a basis for x. Like I mean, just the biggest. What would be the biggest independent set in this matroid if G is connected, let's say? Yeah? Exactly, yeah. Right, so of course if G is not connected, then like it's a spanning tree in each component or something, right? But yeah, so your bases are corresponding to spanning trees. Now, okay, here's a, connecting to this, this other definition we had over here. So we haven't talked about circuits really, right? So any idea in this matroid, what would be a circuit? So right, a circuit is a dependent set, which is minimal with that property. So you can't delete anything and stay dependent. Actually, what are the, yeah.
Cycle?
It's going to be a cycle, yeah. Yeah, because, you know, to make it dependent, it has to not be a forest. So it has to have a cycle to be dependent. But now, if it has a cycle plus other stuff, I could just delete some of the other stuff and it would still have a cycle. So basically, yeah, the circuits are the cycles. Okay. Okay, so in a graphic matroid, your circuits are cycles, your bases are spanning trees, etc. Okay, any questions about that? Okay. Okay. So let me tell you something kind of interesting about matroids. Have any of you heard of greedy algorithms before? So I love greedy algorithms because it's so easy, right? You just keep picking the best thing. Keep picking the best thing, and like, you know, anyone can do it, right? But here's the problem with greedy algorithms. They usually don't work. I mean, well, they'll give you something, but like, it's usually going to be garbage, right? Because usually you have to like actually be smart when you pick things. Right? But here's the magic of matroids. If you're picking things in a situation where the things you're picking from actually are elements of a matroid, you don't have to be smart. You can just do it really stupidly, just greedily, and you're going to win every single time. So, so maybe let me make this a bit more concrete. So yeah, so here's I guess a problem. Let's say X is a set. I is a subset of 2 at the X. And let's say W is like a weight function. We're just going to use non-negative values because it makes it simpler. But everything I'm saying can actually be adapted to using negative values as well. So, so yeah, it's just going to be easier for the beginning to think about non-negatives. So yeah, so this is a weight function. Okay, and let's say my goal is to find a set Y in I of maximum weight. So where the weight of I is like the sum of the weights of the elements, or so the weights of Y. And this is like the type of thing we've been doing all the time, right? Like, for example, X could be all of the edges in a graph, and I could be the set of matchings. And then this is just like find the maximum weight matching, right? You know, so this is a super general problem. Of course, like something like maximum weight matching cannot be done greedily. If you try to do it greedily, you're going to fail. But so in other contexts, though, like if this thing makes a matroid, so I guess my theorem is if xi is a matroid, then the greedy algorithm for this problem, which is just like, keep picking elements of highest weight. So just to explain what it is, so pick elements. Well, I guess you start with y equals the empty set and add elements of max weight, preserving the property that y is in I in each step, right? So this algorithm always gives the right answer, always finds the max weight set. In I. Okay, I'm not sure if it's clear what I mean by the greedy algorithm, but you start with the empty set. You find the maximum weight element among all of them. If there's a tie, you don't care, just pick one of the max weight things, put it into this set. Then I go through all the elements again. I find the maximum weight of an element that I could add to my set while maintaining the property that it's in I, right? Because some things may, if I add them to the set, may break this property, and I don't add them. Right? So I take the biggest thing that would keep me in I, and then I do that again, do that again, do that again, until I'm stuck and I can't add anything else. So there's actually like a converse to this as well, where, so on the other hand, if it's not a matroid, then there exists a weight function W such that the greedy algorithm will fail to find the best solution. Okay, so in some sense, actually, matroids are exactly the structures where greedy algorithms always work. Okay. Is it clear what that theorem is saying, basically? Okay, well, let's prove this. Let's prove the first part first. So assume it's a matroid. Okay, so one thing that's kind of clear is that the solution to this maximum weight problem will always be achieved by a basis, because like if you have an independent, because this function is non-negative, so since the weight, the weights are non-negative, the optimal set must be a basis. Okay, when I say a basis, if I just say a basis without specifying a set, what I mean is a basis for the whole matroid, so the basis for X. Right? Because if I had a set that was smaller than a basis, so it's not maximal, I could add something to it which keeps it independent, and that could, I mean, that might, if the weight of that thing was 0, it would just keep the same weight, or else it's going to get bigger. So I might as well assume it's going to stop at a basis, basically. So here's what I claim. So I claim that at every step of the greedy algorithm, so if, let's say, Y is the set constructed so far, then there exists a basis B of max weight such that Y is a subset of B. Okay. And if this is true, then it's going to be good, because this means that once we get to the end and we've constructed a basis, then there exists a basis of max weight that contains that set, but then it just is a basis of max weight, like when we get to the end. Okay. So at the start of the algorithm, we have Y is equal to the empty set. So obviously it's a subset of everything. So the statement is true. At the start, right? So this is like the basis. We're doing kind of an induction here, right? So now let Y be a set constructed at some point in the algorithm. And let X be the next element that we're adding to Y. So it's the next element selected by the greedy algorithm. So yeah, we're kind of going by induction on the step of the greedy algorithm, right? So I guess by induction, there exists a max weight basis B that contains Y. And now our goal is to prove, so we want to find a max weight basis that contains Y union X. Okay. Is it clear what we're doing? Yeah. So at the beginning of the process, it's the empty set that's contained in a max weight basis, obviously. And now we want to show if the statement holds up to one step of the process, the greedy algorithm, then it holds for the next step. And yeah, this x is like the next thing I would add to y in the greedy process. Okay, so there's one very, very easy case to consider, which is like, okay, what if x is in B, right? And then we're just good, right? Because if x is in the set B, then it's just like, okay, now y union x is still a subset of B, and we're good, right? So if x is in B, then y union x is a subset of B, and we are happy. So we assume x is not in B, right? Okay. So at some point, we have to use this property of being a matroid, right? So here's the thing. Think about the size of this set and the size of, or yeah, okay, this is in this other case. So like, think of like y union x, and think of B, right? So like, okay, B is some basis. Y is living inside of B, right? But then now this x is outside of B. If y union x is smaller than B, then by my property of a second property of being a matroid, if y union x is smaller than B, I can keep adding things from B into y until they get to be the same size, until it gets to be a basis. So like since y union x, remember like the greedy algorithm always maintains an independent set. So at every stage of the greedy algorithm, we have an independent set. Since it's independent, like if B is bigger than y union x, or maybe I should say as long as, like, so just do sort of a loop, right? So as long as the size of B is bigger than the size of y union x, we can add elements from B into y union x, maintaining independence. Right? This is by property 3 of a matroid. I'm not sure if that, okay. Well, so you imagine you keep doing that, right? So you keep adding elements into this set until it becomes as big as a basis. At that point, you've got a basis, a different basis, B prime. So at the end, so once you get to a set of size, the same size as B, then you found a basis B prime containing y union x with the property that the only element of this B prime that is not in B is x. So such that if I take B prime and take away x, it's a subset of B. I sort of hate writing proofs involving matroids and trying to explain them because it's a lot of just like set notation and stuff. But hopefully the concept is sort of clear. Like, yeah, if X was in B, I would already have a subset of B and I'd be good. So it's not. Now what you should do is use this third property of a matroid to take things from B and add them to this set to augment it until it has the same size as B. At that point, it's a basis because it's independent and it has the same size as B. It must be maximal. Otherwise, I get a bigger basis. All bases have the same size. So then you get this basis B prime. But during the construction of B prime, the only element that we ever added that was not in B was X. Right? Because we kept taking things from B, like Y was a subset of B, and we kept taking things from B and putting it in. And so this is the only thing that's not in B. And notice that B prime and B have the same size. So there must be a unique point, let's say X prime in B, such that, like, if I take B and I take away X prime, I get the same thing as B prime, take away X. So if we go back to this picture, like, basically, I start with Y union X. I keep adding things from B until I can't, until it's the same size as B. But at the end, basically, there must be only one thing in B that's left out because yeah, B prime and B have the same size. So yeah. So at the end of the day, what you have is like, well, I don't know how to draw this, but it's kind of a really boring Venn diagram where like B prime and B are pretty much the same thing, except there's like 1 point different on the two outsides, right? Okay, but I claim that B prime is a maximum weight basis. And then we'll be done. Because Y union X is a subset of B prime, because I just got it from starting with this and adding stuff. So how do I know that? So the weight of B prime, if I sum the weights of the elements, it's the same thing as the weight of B, except take the weight of B, take away the weight of X prime, and add the weight of X. Right? Because these sets are the same. So I take the weight of this stuff, which is the same as taking the weight of B, take away X prime, which is that. And then I add the weight of X. And I want to say that this is at least the weight of B. How can I conclude this? Like, how can I get this inequality? So we haven't used anything about the fact that we're using the greedy algorithm, actually. So the key observation is when we chose to add X to Y, X was the next thing in the greedy algorithm. X prime was available to be chosen. Because X prime is like not an element of Y. It's not even an element of B prime. So like X prime was a candidate. We didn't choose it. We chose X instead. If we chose X instead, it must have higher weight, or at least as big of weight as X prime. So this is because the weight of X is at least the weight of X prime because X prime was available when we chose X. So this is I guess by kind of greedy. By the fact that we did a greedy choice. Oh, actually. Okay, anyway, the point here is that the greedy algorithm always finds the best solution in a matroid. Yeah?
Because after we chose that x outside, we were then like restricted to be in that basis. Is that still gives us double bounds?
Yeah, so, well, so yeah, so we had the set y. There was, by induction, there was some max weight basis that contained it. We chose an element x to add to y that was outside of that basis. And what we've kind of showed is that if you extend that set to a basis, it's got to have max weight as well. Well, no, if you extend that set to a basis by adding things that were from B, then it must have max weight as well. I don't really know how. I guess in some sense what this is going to tell you at the end is that these elements must have probably had the same weight. That like B, because B and B prime, like B was supposed to be a max weight basis. There's no way B prime could be strictly higher weight, because then B wasn't a max weight basis. So yeah, anyway, these must have been actually the same. What must have happened basically is that there's like two choices you could have made, and you made one that like screwed up your previous basis that you had, but then you can find another one just as good that contains it. I don't know if that answers your question at all, but okay. Okay. Well, okay, let's prove the second part of this, that if it's not a matroid, yeah, okay. There is something I'm missing in this hypothesis. So, isn't there? Yeah. So what this should say is that if it's not a matroid, but it satisfies condition 1 and 2 of the matroid condition, but not the third one, then there's a weight function where it fails. So maybe let me kind of clarify this. So we claim that if xi satisfies conditions 1 and 2 of a matroid, but not the crucial one, 3, then there exists a weight function W such that the greedy algorithm gives you the wrong set. So So yeah, what I wrote here was technically not quite correct. What I want to assume it has the first two conditions and doesn't have the third. The first two conditions are, yeah, very simple though, right? So here's the weight function. So since it doesn't satisfy the third condition, so since 3 is violated, there exists y and z in I such that y is less than z and y is smaller than z, and there doesn't exist a little z in z minus y such that y union little z is in I. All right, so that's what it would mean for that property not to hold. Okay. So let me give you the bad weight function. So let's let epsilon be small. And let's define the weight of an element, let's say x, to be equal to maybe some intuition here. What I want to do is trick the algorithm, like the greedy algorithm, into picking, like, I know that y is smaller than z, right? So I want to like entice this algorithm to pick elements of y. It's going to keep picking them, keep picking elements of y. And then at some point when it's picked all the elements of y, I want it to get stuck. Whereas actually if it was smarter, it would have picked all the elements of z and ignored y completely. So what I want to do is set the weight of an element to be 1 plus epsilon if that element is in y. I want to make it 1 if that element is in z, take away y, and 0 otherwise. Okay, and we'll pick the epsilon in a second, but just make it kind of small, right? So yeah, if you were doing the greedy algorithm, you would just blindly start picking elements of y, right? Because they have the biggest weight. And every time I do that, you know, well, actually, if at some point every time I do that, it's going to stay independent because it satisfies condition 1 and 2 of the thing. So every subset of y is independent. So like, yeah, as long as I keep picking things in y, it'll stay independent. And so the greedy algorithm will find so the greedy gets a weight of 1 plus epsilon size of y, because the thing is, once it's picked everything in y, then there's nothing like once it's done that, by this property, there's nothing from z that it can pick, and everything else is weight 0. So good luck with that, right? You're not going to get a higher weight picking those things. So you're going to get exactly that weight. But if I just took things from z, so like z itself has weight at least the cardinality of z. It could be even higher if z has some common elements with y, then it's even bigger. But yeah, it could be that. And then now just pick your epsilon, because you've got a bit of a gap here, right? So just pick your epsilon a little bit bigger than 0. And yeah, this will be a higher number than that. So z will be better than 1 plus epsilon y. So yeah, so for small epsilon, okay. Right, so yeah, basically, yeah, these are the only things where the greedy algorithm always works. Probably don't really have time for anything else. Let's see. Maybe just like to now connect this back to this example we had of graphic matroids, right? So what this means is that suppose you wanted to find the maximum weight spanning tree in a connected graph. Let's say you want to find the maximum weight spanning tree. Well, the graphic matroid's a matroid, right? So what you should do is just do it greedily. Pick the highest weight edge, pick the next highest weight edge that you can without making a cycle. right? And just keep greedily doing that. So yeah, using this kind of, well, this is assuming all the weights are positive. But then you can also solve like the minimum weight spanning tree problem as well by just saying like, okay, suppose you're trying to find the minimum weight, take your weights, multiply them by -1 and add some big constant so they're all positive. Now finding a highest weight is finding the minimum weight. It's kind of the same thing. Maybe a bit of history like so yeah. So corollary is that the greedy algorithm works for finding either max or min weight spanning trees in graphs. Okay, and in the setting of spanning trees, this is known as Kruskal's algorithm. Okay, so you may have heard of that in like a graph theory course or something. If not, then it doesn't really necessarily matter. But yeah, so so this basically just generalizes. So this was, I guess, known before people were talking about matroids, and this just generalizes it to like any matroid. Okay, so yeah, I think that's all for today, and I'll see you guys next week.